Hello everybody. It's been a while since I made a video related to dynamics topics, so I'm here with a video which relates to the topic of kinetics of particles using our theta coordinate system or polar coordinate system. Okay, so let me tell you what's given in this problem and what we are trying to find. So the mass of this ball, as you could see here, is given to be 0.5 kilograms. And as you could see, the particle is confined to move along the smooth vertical slot here, right? So this is this vertical slot, and there's no friction involved. Okay, due to the rotation of the arm OA. So as you could see, this arm OA is rotating. In this angular speed that you see here, this theta dot that is given to be 2 radians per second happens to be constant. So this is rotating at a constant angular speed of 2 radians per second. What we want to find is that angle for the position corresponding to theta equal 30 degrees. We want to find the following. We want to find the force that this the force of the rod on the particle, force of the rod on the particle, meaning rod OA. Okay, I'm going to draw a free body diagram in a minute, and also find the normal force of the slot on the particle. So there would be a force that the slot exerts on the particle, normal force of the slot on the particle. So based on what is given, guys, actually it's more convenient to use the r theta coordinate system as opposed to nt, normal tangential, because of the nature of what's given. So actually, let me draw a free body diagram for you guys. So let me start with the known weight, which would be, so the weight would be 0.5 kilograms times 9.81, right? So that would be 4.905, right? Newtons. So this is this guy, right? So now, what do we mean by the force of the rod on the particle? Force of the rod on the particle would be this force here, which would be perpendicular to the rod. And I'm going to call that actually F. All right? And let me put in a different color here the next force, the force that, the normal force of the slot on the particle. So that would be this force, which actually could be either pointing to the right or pointing to the left. Actually, the problem has to state that, let's assume that the particle contacts only one side of the slot at any time. Now, I can pick this direction. If I get a positive answer, then the direction is okay. If I get a negative answer, I just change the direction. All right, so how do we go about finding these two forces? Remember, this is the two unknowns here, right? N and F. Now, first, let's define our radial and transverse direction. You guys recall that radial axis is actually the extension of the R, right? Which is defined here from O to A, right? And then transverse axis is perpendicular to that. So this will be the theta axis. Okay? So once you define R and theta, then you're ready actually to go ahead and find your radial acceleration and transverse acceleration. And that requires a little bit of work and a little bit of, differentiation. So you guys know that, first of all, radial component of acceleration is equal to R double dot, right, minus R theta dot squared. and a sub theta is r theta double dot plus 2r dot theta dot. So what we have to do is to go ahead and calculate what is r and what is r dot and r theta double dot. Now fortunately, since theta dot is constant, theta double dot happens to be 0. Angular acceleration is 0, right? So this term actually is going to be 0, but we have to worry about the rest of the terms. So let me start with r. How could you define r? Look at this triangle here. If this is angle theta and this is r, and this is 0.5, by the way, this is fixed, right? We could say that cosine theta is what? 0.5 divided by r, adjacent over hypotenuse. So this becomes 0.5 over cosine theta, which eventually becomes 0.5 secant theta, right? So r is equal to 0.5 secant theta, which we could go ahead and calculate it actually at theta equal 30 degrees. But actually, let me wait till I go through the differentiation. So what is r dot? So be careful, guys. You're taking r dot means rate of change of r with respect to time. So that means that you take the derivative of secant theta, which as you know is secant theta tangent theta, right? But don't forget the derivative of that with respect to time, right? Because remember, we're taking the time derivative, so you have to use the chain rule. Then r double dot, guys, is going to be factor the 0.5 out. Now this is going to be actually interesting because now we are dealing with 3 terms here, so we have to use a triple product rule, which means just take the first derivative of the first term times the second term. So derivative of secant theta is what? Secant theta tangent theta, right, times the second times third, plus first, which is secant theta. By the way, I did forget actually as I was doing this, the important thing, which is actually the derivative of secant theta is secant theta tangent theta theta dot actually. So let me rewrite this for you guys. Sorry. So this is what you have to be careful. Derivative of secant theta is secant theta tangent theta theta dot times the second times third, plus derivative of tangent theta, as you know, would be secant squared theta times theta dot. So that's derivative of tangent theta times first times third, and then finally plus first second times the derivative of the third, which is theta double dot. Fortunately, theta double dot actually is 0, so this third term is going to be 0. But you see, this is going to be rather bulky term here. So r double dot becomes secant theta tangent squared theta, theta dot is squared actually, and then plus secant cube theta dot is squared. So now you can go ahead and plug in theta equal 30 degrees in each case, because remember, we're doing this at theta equal 30. And use your calculator and figure these out. For example, R becomes at that instant, what, 0.5774 if you calculate it. And the unit right now, as you could see, is the meters. Okay, what about R dot? Again, just plug in the information you have, like what is theta dot is given, secant 30, tangent 30, right? So R dot should be about 0.6667. That should be meters per second. And then finally, if you plug in into this equation the information you have, R double dot becomes 3.849 meters per second squared. Then the next step, guys, is to come here and plug in for R double dot, R, and theta dot squared. So you have everything that you want. You have R double dot, and so on. So go ahead and find your radial component of acceleration, which happens to be 1.5396. That would be meters per second squared. And finally, the 2r dot theta dot remember that theta double dot was 0, becomes 2.667. So this is very important, guys. The goal was to find this acceleration. Now we can apply the second law, which is basically looking at the free body diagram. So what I want to do actually here, guys, to erase this portion so I can finish up in the same page instead of going to the next page. So let me just get rid of this part, right? Remember that the weight is 49.05. There's no friction. So now look, guys, what I'm going to do, I'm going to start summing forces in the radial direction, and that should give me the n value, this force. Summing forces in the radial direction. The reason I do that, and that's equal to what? Mass times acceleration in that direction. The reason for that, of course, is because F is perpendicular to radial, or is in the transverse direction, and it's not going to have any component along that direction. And keep in mind that this angle is 30 degrees, right? So you can use that. This is the positive radial direction. So here we go. Summing forces in the radial direction, we have n cosine 30, right? Minus how much of the weight is going to fall in the radial direction. It turns out that that would be sine 30, right? 4.905 sine 30 in the negative direction, and then that's equal to 0.5 times this radial acceleration that I calculated for you here, 0.5396, right? So go ahead and solve for n, and n is going to be about 3.72 newtons. Notice that I got a positive answer, which means the direction that I selected is right. Now, the next thing I want to do is to look at forces in the transverse direction equal to mass times transverse acceleration. So, in that direction, I have F. By the way, this is the positive transverse direction, right? Positive theta. Okay, how much of n falls into the transverse direction? It happens to be n sine 30, and that would be actually in the negative direction. Keep in mind that you know what n is, right? And you can plug it in here. And then the weight also has a component, would be 4.905 times cosine 30 equal mass times acceleration, 0.5 times what acceleration? This one, transverse acceleration. Okay, guys, sorry it's getting too messy here, but you can go ahead and calculate the force, and that happens to be 7.44 newtons. I hope I didn't confuse you. Remember, the key, guys, is to be able to get the r dot, r double dot, theta double dot. Fortunately, theta double dot was 0 here because theta dot was constant, right? And then determine your radial and transverse component acceleration, and then just apply second law in the two directions. Okay? As always, thanks for watching and listening, and if you like the video, you can always subscribe. Thank you.